floor is yours.
Thank you, Vasilis. So, hello everyone. Today I'm going to talk about my experience, and I will particularly devote my talk to robot in contact operations, how we can overcome this difficulty in a practical task. So on this slide, I would like to present all the aspects of my research, what I'm targeting on, what I was working before, and what I'm targeting to do in the future. I'm dealing with the different types of the robot, with the serial, parallel, consecutive, cable-driven robots. For these types of the robot, I always consider different calibration problems, like a type of the robot, type of the model, its model-based, model-free, real-time calibration, and integrating their geometric, dynamic, elastostatic model. And in future, I would like to address also friction and wear conditions, and combining all these always with the working scenario, with the technological process, with the human robot interaction, applying it to industrial tasks, to medical tasks, and potentially in agriculture, and to make the all things suitable for practice. Just so addressing different sides of the control, from the advanced model-based control that is based on the models developed in my research, with the real-time feedback, to intelligent control and interactive control using mixed reality interfaces. So here it's just brief my career. So I started my career in Belarus, and I was working on design of experiment for robotic calibration. After I moved to France, where I spent 7 years, and my PhD topic was on the stiffness modeling for robotic manipulators, and I'm continuing doing this, but research in this direction. So after for my postdoc, I considered on the industrial robotics and work a lot on geometric and elastostatic calibrations. These two parts I will present today, and further in 2015 I moved to Russia, and there I launched 4 new topics for me. It was MSA technique for stiffness model, human-robot interaction, interactive control, and trajectory planning. And since 2022, I'm at University of Lincoln, and so here the new challenge for me is to work on the mechanism with embodied intelligence. Let me start from the motivation why I start working on the contact operations and what it goes for us. So usually when we talk about the interaction of the human with the robot, about the machine in different tasks, we have a reaction force from the technological process to the robot, from the human to the robot. And in most of the cases, we think that this is disadvantage for us. And that's true if you're talking about industrial applications. These force affect on the accuracy, and we need to do something with this. So these forces, this inaccuracy that we get, it's mainly due to flexibility of the robot, due to elasticity of the components we have there. And the only way to consider these and to improve the model, the control of the robot, is to predict these deviations from the target and take them into account in our model. So that we can do through stiffness modeling. And I should mention that the stiffness modeling is important both for serial heavy robots, where the stiffness is high, but the load is high, and the external force in the technological process is high. And also for parallel robots that's not heavy, but their cross-section is low, and so for the same effort of 10 kilograms, you might get very essential deviation from the end effect for the manipulator and effector. So there are 3 main methods in robotics to work on the stiffness modeling. First of them is, I would say, the most reliable finite element analysis, but we cannot do it in a real time. So usually we use it only for validation. And in my research, I use this not only for validation, but also to estimate precisely the model parameters. And I will address a little bit on this one. So another approach is matrix structural analysis. It's known from structural mechanics, so this is but it's not yet suitable for nonlinear stiffness modeling, while I also have essential contribution to this one, and if someone will interest, I will have at the end like a 20 slides to present completely this topic. And from my point of view, the best one, and this it's honor for me to be one of the co-designers of this approach, virtual joint modeling that extend the classical rigid body model and is suitable for nonlinear stiffness analysis. And I would like to address it now. Okay. In virtual joint modeling, basically, we represent our classical geometrical model, and we replace the flexible components like links, actuators, robot base with the perfect rigid component describing geometry and elastic spring that take into consideration the elastic properties of these link. So here, for example, how we can represent the Stewart platform. So we have elastic link. We represent them with a rigid link and perfect rigid link and virtual springs, actuators, virtual springs, and passive joints. They are passive. They don't have any elasticity, so they will keep them as they are. So here there is a complete library how we can transfer the components of the model into VGM model. So how elastic component transfer to this, how rigid component, and how passive components. So basically what we are addressing here to evaluate the stiffness property, that we address the position of the robot end effector without loading, so given the position T0, and position under the loading. Deviations delta Q and delta theta. So in my presentation, I will use delta Q as a passive joint coordinate and Q is a passive joint coordinate. It's not control coordinates, and theta is virtual joint coordinates. Joint angles, it's geometrical parameters here, so that's why you will not see it. And so all these deviations of the end effector and the reaction in joints, it will create some virtual work inside of the virtual springs, and we'll have reaction due to elasticity, like here matrix K theta that aggregates the stiffness property of the link. So here you see the solutions. Okay, how we can evaluate. So what we did, we developed two basic techniques that can be used for stiffness analysis of the different types of the manipulators under the loading. So on the left hand side you see the numerical routines. So when we can simply combine the matrix and extract the component after the inversion. The disadvantage of this approach is that sometimes we need to invert high rank matrix, because here, for example, Jacobian G theta, this is Jacobian with respect to virtual joints. It's has a high dimension. So if you have a 30 virtual joints of 30 springs in the system, it means that it has 30 by 6 dimensions, and it's can be 80% of the matrix dimension in this case. So while when we eliminate it and go into analytical solution, so this is just mathematical routines, so like with the blockwise inversion, allowing us to get lower matrix inversion equations. That gives us equation in the form where we have the first component describing the basic stiffness property without passive joints. This is actual for power structure, and the second one take into consideration the effect of passive joints. It's clear that adding passive joint decreases the stiffness. That's why we have a minus here in the equations. And with these routines, we can easily get analytical solution even for parallel robots, like for Stewart Platform, for example. With the two-assembly mode, we can get this solution, and we can get a full rank matrix, and we can get rank deficient solution. So that's quite evident that we don't have a reaction on rotation on Z here. That gives us stiffness equal to 0. So from that point of view, we can use also stiffness analysis for to detect the singularities, because in singularity we have rank deficient stiffness matrix as well, while we still can compute them either numerically, either analytically. So in all mechanical structures, we will have errors. Okay, and these errors they will affect on the position of the manipulator. So if we talk about the serial structure, usually they will be accumulated. While when we talk about parallel structures, they will be accumulated for each kinematic chain, and after, when we combine them together, so we will average the errors. While to be able to assemble such a structure that has errors in the kinematic chains, we will need to introduce the force. So we will get preloadings, and we'll have routines allowing us to compute the deviation the and effector due to inaccuracy in the serial chains, and allow us to compute the reaction forces in the each chains and corresponding reaction force and energy. So that solution is obtained using the minimum of energy principle. So all these that works for small deviation. So when we assume that we are in a linear zone and like a force deflection relation is linear, while it's not always true in practice. So sometimes the force deflection relation is non-linear. You can see in this plot, for example, and it might happen that buckling effect might happen. And I'm proud to be the first one who detected this effect in the robotic structures, and the approach we developed allow us to estimate like a pre-buckling condition and post-buckling condition in mechanical structures. So we know this from the column buckling. So when we apply the force at a certain level, the column doesn't change its shape essentially, but after it's dropped down. The same might happen in robots. And here we're not talking about the buckling of elements, but we're talking about geometrical buckling of the structure that's suffer from instability with a much lower force we need to apply for this. So here, to be able to address the nonlinear stiffness analysis, so first of all, we need to find the equilibrium configuration. And here we are using static equilibrium equations and geometrical constraints specifying the end effector positions, and that allows us to derive iterative procedure, allowing us to get the state for the static equilibrium configuration. So here, what we are given, we're given the position, we're given the shift of the position, so where the end effector moved, and we computing reaction force F and corresponding deviations in the virtual and passive joints. So what is important here, that after the configuration change, we need to recompute the Jacobians, okay? Because the Jacobians should be computed in the vicinity of current loaded configuration. And here we might have a different type of the loading. Some of them might be neglected. For example, the vector G, it's aggregate auxiliary loading. So the loads applied in the node points. It is not always presented. So if we don't have a load presented in the middle of the robot, we can take this out. And the F, it's the force applied to the robot end effector. So, and so after we computed the equilibrium configurations, we can estimate the stiffness property of the robot. So to compute the stiffness matrix, let's estimate this property. So here we goes to this position. So basically, usually people consider like K0 this scenario when we address only the linear zone at the beginning, while the current, if the force is high enough, we can move to the linear shape, and here we will be able to get this. So if you look on the equation that you see here, it consists Hessian matrix. This is the second derivative of the Jacobian of the geometry. So it's derivative of Jacobian multiplied by the applied force, and this is the main difference with respect to linear stiffness modeling. So the effect of the force is integrated inside of these Hessian matrices. So the Hessian with respect to QQ, this is the second derivative with respect to passive joint coordinates, like Q theta passive and virtual joint, and theta theta with respect to virtual joint. So this is the second one. And again, so we can use like a numerical solution and analytical solution, allowing us to estimate the stiffness matrix here. So when we talk about the loaded mode of the robot, we might have both stable and unstable configurations. And that's critical for parallel structures to be sure that we're in the stable one. Because if you're in an unstable one, we can suddenly, the configuration can be changed suddenly without our that's when we don't want. And here, for example, the minimum of energy will correspond to the stable equilibrium, and maximum of energy will correspond to the unstable equilibriums. And in practice, unstable equilibriums we will not see. We can get them numerically. Okay. While any disturbance in a physical system will move us out from this unstable equilibrium. So we need to be sure. So to be able to evaluate which equilibrium configuration we obtained numerically, okay, so we develop the matrix criteria, okay, that is also based on the geometry and the elastic properties of material, and we use singular value decomposition of extended Jacobian of virtual and passive joints. And if this matrix criteria is negative, so it says that equilibrium is stable. So if we found that equilibrium is unstable, so what we need to do, we need to add some noise. We need to add some disturbance and run the procedure again, and it will converge after this to the stable configuration. So here you can see some results. Okay, what we can do with this approach. For example, this is a linear system. So this is with the free-link system. So when we apply loading up to the certain load, so we don't have any deviation of the end effect. But while the force reaches critical value, so the behavior change completely. You see this graphical representation. So we can work in the nonlinear behaviors. So like here, we don't have a buckling key effect, but nonlinearity that change the stiffness properties, and we can properly evaluate and predict the stiffness under any load we applied. And also we can have a nonlinearity and buckling effect. Nonlinearity happens at the beginning, and after we can observe buckling effect, the change of this of the plane. So the buckling might happen in the plane of nonlinearity, or the buckling might happen in the orthogonal plane as well. What else we detected? That there is another source of singularity. So we're always talking about geometrical singularity, but in practice we might have also elastostatic singularities. That's under the loading, the kinematics will fall down from the this yellow zone. So what does it mean? That geometrical singularity that we have there in practice will not be reachable, because the force will move it for this. So if they will have a gravity force, at least the weight of the links, so we will pass for these geometrical singularities where we probably may lose the control. And this path, okay, we can see, we can model it inside of this yellow arrow. It corresponds to the negative stiffness. So we have a negative stiffness along this one. So this that's how the approach works when we combine different chains in it. So we can use it to model the sophisticated robots, okay, serial and parallel. So with the serial, it's easier, but for parallel, when we combine multiple chains, and here we are capable to identify also the backlink effect. Yeah, as you can see, the force is high enough. Okay, but this is for these two particular configurations. But when we approach into the flat configuration, near flat configuration, the force decreases. While we can always estimate the critical force up to which one it's safe for us to operate, because even though we can simulate the behavior before and after backlink, okay, in reality, we'll have some uncertainties, and the backlink effect can happen like 1–2% before or after in terms of the force magnitude, and this will affect essentially on the behavior. So in practice, we prefer to avoid these conditions, but we need to know when it happens to be able to react it. And why we need all these, just stiffness modeling, we want to use them to compensate the technological process. And it's a pity that up to now we don't have such abilities in the robot controls, and we need to design the special precision. So basically, to be able to compensate compliance errors, we need to have our own compensator that has a direct geometrical model that is exactly the same that's implemented in the robot controller, and extended inverse model that contains not only geometrical but also stiffness model that allow us to predict deflections. So in this case, we give a desired trajectory to our compensation algorithm, and we obtain modified trajectory that is different from the target one. But this is the trajectory we are sending to the robot control that ensures that the output trajectory will be close to the target one. We're not targeting to have exactly the same, because in practice it's not possible. We want to be as close as possible. So another topic I want to talk about, it's related to elastostatic calibration, and here we will talk about accuracy improvement, and so what we want to have high accuracy and high repeatability. But when we start working with the robots, so in most of the cases we might have high repeatability only, and while high accuracy is never ensured by the robot manufacturer, for example, or anyone. So we need to target this one. So to be able to deal efficiently with the robot calibration, we enhanced classical calibration technique. If you worked before with the calibration, the traditional calibration procedure includes 4 steps. It's modeling, measurement, identification, and implementation. While from my point of view, one step is missing there. It's selection of the configuration that we will use for measurement. And so we introduce here additional step between modeling and measurement. It's called design of experiment, allowing us to improve the the efficiency of calibration. Here we can target to reduce the errors or reduce the number of experiments we need to get sufficient accuracy after the calibration. That's basically what we did, and I will talk about this. So, and when we address the elastostatic calibration, we have some additional constraints and particularities compared to classical geometrical one that everyone knows. So, for example, on the modeling step, we need to integrate also flexibility in it. We need to take into consideration applied force, and that gives us much more parameters in the model that we need to address, and not all of them they're decoupled, and we're capable to decoupled, and I will talk about this. And also influence of the gravity, so we need to consider this. On the measurement step, we will rely not on the single measurements of the position, but on the difference. So we need to measure the position with loading, with the two different loadings, or with loading or without loading, and we need to measure the force. And the main limitation are here that the force magnitude is usually limited by the torque we are allowed to apply for the motors. On the identification step, so we need to define much more parameters, and in compensation, as I mentioned already, so we're not able to implement elastostatic model the controller itself. We need to design our own model, and we need also to evaluate the forces here. So here it's a basic equation that we use for geometrical errors mapping. So we use a linearized model with the Jacobian and the set of parameters delta pi we want to get. The mapping of compliance errors, usually we have this equation with the k theta in between. We rewrite it in a similar way as a geometrical one, where A is so-called observation matrix here, and K is the vector of designed compliance parameters, and optimization problem. To solve this, we can write in a generalized form where like a B, its observation matrix either Jacobian or either A matrix, and delta X is the set of unknown parameters. So standard solution and identification accuracy, we can estimate over covariance matrix that estimated in experiment using here. So the difficulty here is how to choose B matrix. Okay, so usually many people choose this randomly. Okay, while that's affecting the final quality, sometimes bad choice of the configuration can even decrease the calibration accuracy. The difficulty in elastostatic configuration is we have twice more parameters. We have not only configuration, but also the loading that we need to consider as a parameter. So to be able to work with the meaningful values, meaningful meaning of what we are doing, we propose a test post based approach that estimate the accuracy of the calibration procedure. Okay, in terms of the technological process we are going to perform on this robot, for example. So let's imagine that we have a target position that's shown here, and technological process move the end effector with the force F to some position. What we will do in this case, we will compensate it. Okay, so we will get an opposite configuration with the minus delta Q for this one. So the green one, this is what we are giving to the robot, and basically we move to some position that is close to the target one, but not never will be the same. And we have some distance rho, so the delta p. So that we introduce as a performance index here, specifying the efficiency of calibration. And we want to minimize this distance from the statistical point of view. So we estimated, okay, from the model data and proposed these performance measure that has two types of the matrices, like a BI and B0. B0 is our test configuration, in the conditions in which the robot will perform the operation. So basically, this is the area of the robot where we want to have the highest precision. So we don't need always to have a high precision within the entire workspace. So if the robot is performing in a small area, for us it will be sufficient to have a very good accuracy here, while the moderate accuracy in the entire workspace. And so this performance measure, rho square, it gives us optimization problem that we need to solve subject to the constraints of the geometrical constraint and force constraints we can apply. So this is like the typical constraints, for example, that we use for robot calibration. So when we carry out experiments, so we have a limited zone, so where we can apply force. Okay, we have also constraints related to the measurement visibility, so where we can put markers that induce the positions of the orientation of the end effector. Also have a joint limits and so on. The design of experiment techniques is a powerful tool allowing us to increase the accuracy, but it's quite computationally complex. And when we talk about, for example, 12 different configurations. Okay, so we're talking about 6 parameters for the force, 6 parameters for configurations, and it means we're talking about 144 variables, and we will not be able to find the global minimum for this one. So, and to make it easier, so we investigated how critical will be if we will try to use quasi-optimal solutions, if we try to go to the low dimensional plans. And it was not surprise for us that we found that instead of carrying out experiment for simulation experiments for 12 configurations, for 12 different configurations, we can select 3 different configurations and solve the problem 4 times, for example, or repeat measurements 4 times, and the accuracy will be roughly the same if we will use 12 different configurations, while these save essentially the time for us. And if we're talking about real experiments, having the less number of configurations, it also gives us requires from us less time to carry out experiments, because we don't need to move to other configuration to investigate if we can carry out in this configuration or not. We can simply repeat experiments several times in the same configurations. That's if it gives the same efficiency. And this has also another advantage, that we can eliminate the human factor if the results were recorded incorrectly. We can also track these errors. So like a free measurement configuration from here will be enough and give the good. So this is some experimental setup that we use, for example, in France for robot calibration. So we use a payload, we use a force measurement, so we applied maximum force, and here we use 36 measurement points in total. So I will not present the result now, I will present them later, and now I would like to address the another issue. So it's related to the estimation of the parameters. For example, if you address the link stiffness, Okay, so for example, I took here the model of the from real robots, and for this link, I have sophisticated model from the CAD. Okay, and I can calculate this, and this key is obtained from the CAD. While if we will try to emulate the experiment. So we want to obtain this data from real world, so not from the simulator. So we carry out experiment, apply force, edit measurement noise that we will always have from the measurement data, and try to evaluate these values. So just what we obtained here. So which property we want to have? That the stiffness matrix should be positive defined. Okay, positive defined. While the first component K11 is negative already, so it's not a positive defined. So the matrix should be symmetrical. So we don't have a symmetricity here. It's approximately, but not exactly symmetrical. And also we have 36 different parameters. While if you remember on the first slide, we had a lot of zeros. Okay, so if you will evaluate the ratio of the parameters we estimate with respect to the noise, so we will be surprised that some parameters they are lower than 1. So what does it mean? That the noise contribution to our estimation is much higher than the magnitude of the parameter we extract from these. And that happens with the simulated data, and approximately the same it happens with the real data we get an input. And so based on these, so we can conclude that probably we shouldn't believe in everything we get from the real experiment, and we should properly filter the data. And one of the idea was here just to introduce additional metric, okay, metric to parameter to noise ratio that gives us accessibility. So, and going in general to the elastostatic parameters identification of the robot. So the general solution can be written in the following way, where we have many redundant parameters. So when we consider only only joint elasticity, we have 6 parameters and we don't have any problems. While when we assume that not only link or joints but also link might be flexible, each link basically introduces 36 parameters, and we will go over 250 parameters for traditional serial manipulator. So, and here, these parameters we will need to decompose into identifiable, that we're capable to identify from the experimental stuff, non-identifiable, that's not important and we can take them out, and semi-identifiable, that are not identified separately, but they are grouped with some others, so we need to keep some parameters and another one fix them. So, and apart from these, as we already saw, that some parameters can be treated probably they're identifiable from the mathematical routines, but from practical point of view, they are not significant. So, and here we are introducing three other groups inside of identifiable parameters. It's practically identifiable parameters that have a statistically significant meaning in the model. Practically non-identifiable parameters in which values we cannot believe from at least this experimental setup. So we are not capable to, and keeping these parameters in the model will degrade the quality of the result. And practically semi-identifiable parameters that are probably identifiable, but with the current experimental conditions or with the number of experiments carried out, so we cannot believe truthfully in this result, and we need either to change the experimental setup or the number of experiments to see if the ratio will be increased or decreased, to keep or take them out. So And we develop a framework allowing us step by step develop the stiffness model that we are able to identify from real experimental data. And in the first step, so when we introducing the model, we need to take into consideration that each link induces us not 36 parameters, but it's symmetrical. It's maximum 21 parameters. So we take into consideration symmetricity property. The second one is sparsity. So we have a lot of zero components, and we can develop approximate model of the link in the CAD and extract the benchmark and use this benchmark. And for the specialists who are working with the CAD model, for example, it's quite easy looking at the model, just say which parameters should be non-zero. And the third step is related to aggregation of different parameters. For example, we have a flexible link and flexible actuator. From point of view of measurement of the end effector, will not be capable to distinguish the deviations in the link and in the joint. So we these parameters are coupled. That's why we aggregate them, reducing these parameters. So this that was the first stage. The second stage, we need to understand which parameters in the remaining model are identifiable, non-identifiable, and semi-identifiable. So the number of parameters that are identifiable we can get from the rank of observation matrix. And if we use a singular value decomposition of this observation matrix, we can extract the coupling between these matrix. So this is basic routines how we get the solutions, and here the rules how we can get the parameters. So basically, from after singular value decomposition, we will have a part of equations that are giving us meaningful values, and the part of equation that given 0 equal to 0 equations, and the general solution and the particular solution P0 we use here. And here on the first step, we decompose the parameters onto identifiable, semi-identifiable, non-identifiable, and semi-identifiable. So identifiable parameters, they will be completely visible. So we change one parameter as an input, and we will have it on the output. Non-identifiable parameters change will not affect on the change of the end effector measurement. So we will not see any of them. While this is easiest part. Okay, the most difficult is coupled parameters. So the group T. So this is the like two rules. Rule 1 and rule 2 allowing us to identify to specify identifiable and non-identifiable parameters, and all the remaining we will put in the group 3. This is semi-identifiable, that's with which we will work later. So non-identifiable parameters we eliminate here. With the semi-identifiable parameters, we will get the corresponding observation matrix A with respect to these parameters, and we will use singular value decomposition, and we will have like a full rank V component and extended component. And based on this, we will compute the matrix L. Okay, the matrix L gives us relation between the components. From this matrix L, we will see the blocks of the components that are coupled. And looking at these components, so we for each block we can compute the rank of this block and select either manually or having some procedure which parameters we want to keep in the model, and the remaining put some constant or to the zeros. So this is this step. And the last step, it's related to neglecting statistically non-significant parameters. After we obtain the model, elastostatic model, we evaluate the noise impact on the parameters, and we keep in the model on the parameters that have a statistically significant meaning. So this is the experiment, and how these steps applied for real robot and what we kept in the model. So after the original model had 258 parameters, so physical approach reduced to 56 parameters here. So so you can see the steps. Algebraic approach reduced to 26. And since we use already intelligence, like some knowledge when we selected the parameters, so we already know which parameters will be small, for example, like compressions of K11 components. So we got all the parameters that are statistically significant, and this is the structure. Okay, which parameters from the link kept in the model. So here is the result in comparison of two different approaches. So reduced model, that's most of the people are used, okay, and what we achieve in terms of the accuracy in a single component and in the position, and complete model that contains 26 parameters. And what I would like to stress here, with the complete stiffness model extracted from the real experiment, we reach the physical limit of that we can have for this particular robot, taking into consideration robot repeatability and the measurement accuracy of the measurement system. We had here, so 10 like 100 microns per position measurement. This is almost the physical limit we are capable to have here. And to be able to evaluate the parameters, like the model, to get a valid model, so we also developed the cut-based stiffness matrix identification technique, allowing us to get sophisticated model. So I'm not going to talk a lot, so this is just the reference for the paper. And another part of the work I did, it's related to work with a robot with a double encoders that induced much more possibility in terms of error compensation, parameters identification. And here the proposed approach allows us to go to the blue zone here in terms of accuracy or on this plot, while the embedded technique with the secondary encoder compensation, this is a green zone, okay, here. And if you are not relying on any compensation technique, will be on the red zone here in terms of accuracy. So we are 3 times more accurate compared to the embedded when we rely on the stiffness model. So that that's the effect of the optimal design of experiment for simple robot calibration. So how the accuracy will look like if you have a random plan, if you have a regular plan, for example, traditional, and if you apply some sophisticated. So this is also so another part of my work that I was mentioned. So I worked in the human robot collaboration, and particularly what we worked with the interaction and extraction the knowledge from the interaction. And here our objective was to understand the nature of interaction and to understand where the interaction happens. And based on this, select an appropriate reaction. So on the left-hand side, you see the video with the framework that detects where the interaction happens, okay, and selecting an appropriate reaction stage. On the right-hand side, you see this more advanced result on the so-called digital skin, when we use only internal sensors and we are using the sophisticated behavior of the robot. We are capable to identify the contact point and the force magnetic contact point with the precision of 1 centimeter. That is a fingerprint. So we're not using any extra external sensors. Here only internal one, and all this works in the real time. There is some visualization delay, but all the system is working in a real time. And another work I did with mainly with my students related to human-robot cooperation. It's related to using a mixed reality to design the control strategy and interaction scenarios with the robots. So we completely emulated the robots in the virtual environment. So we did here with the with the robotic manipulator, with the drones, with the mobile robots. Okay, and we're capable to see what happens in the virtual environment and evaluate if we are satisfied with these solutions. So we will send directly to the robot. So here we merging different technologies. So we're using ROS, we use as a framework that's allowing us to merge different objects, different aspects. So, and the operator here, you can see real robot and virtual robot, how it works to see it. Another part of the work I mentioned, so we don't have the time to present it in details. It's related to matrix structural analysis, and here this approach is mainly developed for complex structures. Like, for example, you see in this example, we have a multiple closed loops. Okay, and we have a standard framework allowing us to describe different components, links, constraints, external forces, and integrate them in a system of matrix equations. And we have a procedure allowing us to solve this in a unique way. So just repeat what I'm doing. So thank you.
Any questions? Any questions from the audience, the online?